Okay, so hello everybody. This is the identity that I had asked you to prove in one of the previous classes. The Zoom updates are being really slow, and I am really sorry for that. And it is really annoying. Okay, so why did we need to look at this identity in the first place? Right? 1 second. Okay, I'll be right back. Let me try to fix the network connection a little bit. Okay. All right. So I'm back. What I did was, am I audible?
Yes, sir.
All right. What I did was I disconnected the Alexa. So we have an Alexa device given by my sister, and you know, the one that says Alexa, play this song, play that song. And I don't know if that's responsible for the slowdown, but anyways, we'll see. So the reason that this identity is important, right? It's when you're trying to prove, derive the Lorenz Force Law, starting from the Lagrangian for non-relativistic Lagrangian for a particle in a external field, right? So you get this term when you evaluate the equation of motion, right? When you write down dp by dt is equal to dl by dx, right? This is the Euler-Lagrange equation of motion. And then obviously this identity is not very obvious at all, right? So if you didn't know it to begin with, you know, you might not quite see the connection. But you have two terms. You have mx double dot, right? That pops up here. Then you have q times e that pops up here. And so if you know the Lorenz Force Law, right? If you're familiar with what it happens to be, then it figures that, well, okay, this quantity should evaluate to v cross del cross a, right? So now, rather than deriving this, what I'm going to do is I'm going to check the identity is correct. Okay. So how can we do that? So let me. Have I introduced the anti-symmetric tensor to you all? Epsilon. I have?
Yes, sir.
Yes? Okay. So I will use the epsilon tensor to do this. Okay. And so you can see that if you take the curl of A and you take the ith component of this object, it can be written using the Einstein summation notation and the epsilon tensor in this way. So because the epsilon tensor is completely anti-symmetric, right? So let's say you want the x component. So then this will be epsilon x jk dj ak, right? Now the only non-zero components of epsilon, when one component is x, the other two components have to be y and z. So you have x, y, z, right? And then this has to be dy az, and then epsilon x zy dz ay, right? These are the only two non-zero terms. And this, the first term is going to be +1, and the second term is -1 because it's an odd permutation of the indices. So you get dy az minus dz ay, right? Okay. So now we have this expression v cross del cross A, right? So let me write this as v cross B first, okay? Where B is equal to del cross A, right? So v cross B I will be equal to epsilon ijk vj bk, right? So this is a derivative. Instead of a derivative, if you put a vector, you will just get that vector as a multiplicative factor, right? Now, what is B? B k is equal to curl of A k, right? So what is this? This is going to be epsilon k. Now I'll use two other indices. I can't use the same indices which I've used before, right? So this is going to be epsilon k mn dou m an. Okay. And so finally, I can write down v cross del cross A, the ith component of this is equal to epsilon ijk, then epsilon k mn and vj bk. So bk, instead of bk, I'll substitute this expression, right? So I've got epsilon k mn vj dman, right? And now this expression doesn't look any simpler. So it might seem that we have simply increased the level of difficulty, but now what we can do is we can use some identities. Okay, so I'll tell you what those identities are. And to just make our life a little bit easier, what we will do is I will write epsilon k mn with the m on n on top with the raised indices. This is just for ease of notation. Remember, these are all spatial indices, so raising and lowering doesn't affect anything, right? Because you're just using the identity, the delta, Kronecker delta to raise and lower, right? So this quantity, epsilon ijk, right? I can write epsilon ijk is equal to epsilon kij, right? Using a cyclic permutation. That's what I've done over here, right? And I've just taken the k and raised that index. Okay, so now this quantity has a sum over k, right? Because k is a repeated index, right? So this is contracted over k. And now this is equal to the following expression: delta mi delta nj minus delta mj delta ni. And I think that's it. Maybe there is a factor of 2. You can check. Okay, so I'll just put a empty spot in there. So this is a very, very important and very useful identity. Okay, so you should know this. And so if you insert this expression now into this, what do you get? So we take this guy, right? So this is the sum of the product of these two epsilon tensors. And very hot here, hot and humid. And then we put the rest of this expression in here, Vj dman. Okay, and it's understood that wherever there's a repeated index, you have a contraction. And like I said, there is some factor which we will check what it is. Okay, so now if you contract these terms, the first term delta m, right? The contraction is easy. Vj delta nj, this will just give you Vn di an, right? And the second term will give you j is contracted here, so you will get dm, and then m, this, sorry, Vm, and this will become dm, and this will become ai. Okay. Just right. Okay. So gradient of v dot a. Okay. So now if you look at this expression, and now let's ask ourselves about this is the RHS, right? Now let's look at the LHS of the expression, gradient of v dot a. Okay. So this can be written as gradient of Vj aj, right? And the ith component of this will just be d of I Vj aj. Right, so that will give you Vj d of I aj plus aj d of I Vj. Right? Now, one of those terms is here, right? Right, these two terms are the same, and then I'm getting one extra term. I don't know why I'm getting that. So let me go back and check my calculation one more time. V cross del cross A. So let's see, is equal to V cross B, V cross B I, equal to epsilon I j k, V j B k. B k is equal to curl of A k, epsilon V cross curl of A I. Okay, looks good so far. And then this is anti-symmetrized over the ij indices. So that's good. Okay, this expression is different, right? Something I did wrong here. No, this is fine. This is perfectly fine, right? And then the second term will be Vm. Yes. I think this term is also, this term is incorrect. Let me write that down. So give you Vm. No, it will give you the same thing. Sorry. It will give you Vm dm ai. Okay, so I don't know quite what happens to this term. Let me see. Did we make any assumption about the gauge fixing back there? Here we didn't make any assumption about the gauge fixing, right? So, Sai, you said that you had worked this out, right? And how did you do that?
So I use the identity A cross B cross C is equal to B times A dot C minus C.
Oh, right. Yeah, so I guess You can just do that. So you can write this as gradient of v dot a minus, what was it?
A times del dot v.
Right, okay. So the thing is that, why is the second term 0?
Magnetic field does no work.
Magnetic field does not work. How is the work coming in here? I'm sorry, but I'm not, I guess it's maybe something very, very basic. And so, yeah, okay. So anyway, so this is 0 for some reason. Why is this 0? I think what Sai is saying is roughly correct. Because so if you have a particle in a magnetic field, its velocity, it will move in circles, right? It will move around. And so when it moves in circles, the velocity will have a non-zero curl. Or so the divergence of that velocity should be 0. Okay, but again, this is not a very good justification. Okay, there should be some more clear justification for why this term is 0. Otherwise, we should actually include this term in the Lorenz Force Law. So the Lorenz Force Law should be V cross B plus A times divergence of V. And then we should solve the equations of motion self-consistently to show that when we include the Lorenz, so what does the Lorenz Force Law become? Mx double dot. So we get Mx double dot plus QE plus this term, right? Plus QE, and then plus Q times V cross B plus Q A times the divergence of V, right? So this term is present. It's not. It doesn't vanish identically due to algebra, right? So so yeah, one would have to solve this equation of motion and show that some self-consistency requirement implies that divergence of V should be 0. Or is it going to be 0 because of the Euler equation? Yeah, so divergence of V will be 0 because this corresponds to conservation of momentum. Okay, so if you have any closed surface S, and then you ask what is the total momentum that is coming into the surface and what is the total momentum that is coming out of the surface, right? So the flux of momentum, is equal to surface integral of P dot dA, right? And by the Stokes theorem, we know that this is equal to the volume integral of divergence of P times dV. And since we are in a non-relativistic setting, P is just equal to mv, right? So this becomes equal to m times integral of divergence of V dV, right? And so conservation of momentum, but then you have an electric field that is doing work on the system, so the momentum need not be conserved. So I'm also a little bit lost. Okay. So the point is that some things which seem simple are not necessarily very simple, because there might be an electric field in this region. If there is an electric field in this region, this electric field is going to do work, and that is going to that might change the outgoing momentum. Right? Particles will be accelerated. So if you consider this is your surface, and you have electric field over here, right? And you consider some particles with momentum coming in, then they can either be accelerated or they can be slowed down depending on the direction, the sign of the charges. And so in this case, obviously divergence of P would not be zero. But if there is no electric field, then yes, it would be true. So this is equal to 0 if E is equal to 0. So anyways, yeah, I mean, this term, whether it should be there or not, this is something that maybe one of you can inquire more deeply into. And what you realize by looking at such problems actually is that electromagnetism is full of unresolved problems, even classical electromagnetism. And so one of those problems is called the self-force problem. And then there are others. So even just by looking at the equations of electromagnetism, if you try to find a self-consistent solution, there are situations in which you cannot do that. You cannot find a self-consistent solution. Okay. Anyways, all right. I think that's enough for this term. Now we'll get back to our particle in an external field and the quantum mechanics of that particle. Okay, so quantum mechanics. External field. Okay. All right. So this is the expression that we ended up with last time. And this is, as usual, our kinetic energy term. Then we have a potential energy term. And then we have a new expression here. Right. And this is the term that will give us something interesting. So what does it do? Okay. So this term, we will solve it for a special case. Okay. We'll look at the case of a constant uniform magnetic field. Okay. So that's what we're going to do first. Now, so, and this is an external magnetic field, right? Not something that is there due to the motion of the particle itself. So for a uniform constant magnetic field, such as, for instance, let's say your magnetic field is pointing up, it's in the Z direction. So B is equal to B naught Z, right? Now, if you want to write down the, what do you call it, the vector potential, which will give you this expression, well, you have several choices, right? You just need something whose curl of whose component will leave you only one surviving component, right? So basically what you want is, so what is this? This is the z component of the curl of A, right? Because this is the z component, that's all that is. And so this is what? This is the z component is dx ay minus dy ax, right? And this has to be equal to b naught, right? So there are several ways to write this. One way to write this is you can say, let's say ay is equal to b naught times x, and ax is equal to 0. Another way to do it is you can say ay is equal to 0 and ax is equal to minus b naught times 1. Okay, you can see that when you put this expression in here, when you take these derivatives, you will get b naught, right, in both of these cases. Another possibility is you can do something like this. Okay, so you can write down, so you're just putting it half and half in ax and ay. So when we do this, this is called the symmetric gauge, right? Right. So it's called the symmetric gauge. And in this symmetric gauge, you can see one thing that, so ax is equal to minus 1/2 y times b naught, and ay is equal to 1/2 x times b naught. So if you combine these two expressions, you can convince yourself that A, the vector field A, is equal to minus 1/2 R cross B, where in this particular case, our B is our constant magnetic field, right? So if you put this external constant magnetic field in here, right? So B will only have a Z component. Since B only has a Z component, and A, so which components of R will contribute? The X and Y component only, right? And those will contribute, and they will contribute in precisely this way. So A can be written as minus 1/2 R cross B, right? This might seem a little bit odd because, I mean, intuitively you're just thinking, well, B is the curl of A. So how can A be written as this? Well, you can, this is for a special case, which is for a constant magnetic field. If you don't have a constant magnetic field, you can't write, because then you will get derivatives of the magnitude of the magnetic field. And so this term we have, right? And I forgot to multiply, I forgot a factor of Q here and a factor of Q over here. Okay. So now we have this term, which is I cube H bar over M times A dot gradient of psi, right? And for the special case of an external constant static external magnetic field, static uniform magnetic field, we can write A. So this becomes QH by M. This is all just a constant. So A can be written as R cross B dotted with the gradient of psi. Okay. Now, this expression we can play around with it a little bit. Why? Because remember, again, B is a constant, right? So now you might remember that for if you have some vectors like this, you can always rearrange the order of vectors like this, right? You can always write C over here and B over here and put a minus, right? Because this is equal to C cross A dot B, cyclic permutation, right? Again, this expression is very easy to see if you use the epsilon tensor. So if you use the epsilon tensor, this becomes epsilon ijk ai bj ck. And now if you look at this expression, it's very clear that you can write this as epsilon kij, right? ak bi cj, etc., right? Because of the permutation symmetry of the epsilon tensor. So this expression that we have over here, R cross B dot gradient, it can be written as minus R cross gradient dotted with B, right? Why? Because again, B is a constant field. If it was not a constant field, you couldn't do this. And so we have IQ h bar by M. This term becomes A dot gradient of psi. So you have a minus sign here and a minus sign here, it goes away, you get 1/2 QH bar by M, R cross the gradient. And so this gradient of psi, you can, so you can just take that whole gradient of psi term and you can put that inside the bracket. You can write it like gradient of psi. Okay. And yeah, just to I guess to correct myself, as long as the gradient operator is only acting on psi, B does not need to be a constant. Okay. So as long as gradient is only acting on psi, you can always change this, because gradient of psi then becomes a vector. That whole expression becomes a vector, and you can just use the cyclic permutation. Now, what is this quantity? R cross the gradient. R cross the gradient, right? You have R cross the gradient. This whole thing is acting on psi. And what is this? This is what we refer to as our angular momentum operator, right? Well, angular momentum operator with suitable factors of h bar n. So, okay. So what is L? L is equal to R cross P is equal to minus I h bar R cross the gradient, right? So this is the expression for the angular momentum operator, right? So in this expression, we have I, we have h bar, and we have R cross the gradient. And so finally, our expression, this expression, copy and paste it in, becomes, again, we'll get one more minus sign, Q by 2M this operator L, so now I can write it as B dot L acting on psi. Okay, you can write it as L acting on psi dotted with B. It's the same thing. It will give you the same expression. So this is what? This is called causes a coupling of the orbital motion, right? Orbital coupling to the external magnetic field, right? So if your angular momentum is non-zero, you will get this term will play a role, right? And this term is also known as the paramagnetic term. And then we have another term which is called the diamagnetic term. And which one was that? That is this expression QA squared by 2. Once again, for the same field configuration, we have Q squared by 2m, and then we write A, the vector A, as R cross B, or minus, we write it as minus 1/2 R cross B. And so we get a minus sign, and we get 8 times m, and we get R cross B squared. Okay. And this expression R cross B squared, again, if you want to evaluate what this will be, we can use our epsilon expressions. So I'll write this as epsilon ijk rjbk, and the second term I'll write as epsilon imn rmbn, right? And so because there is a repeated I, right, that is what gives us the dot product. And so once again, we can write this as our constant, then delta mj, delta nk minus delta mk, delta nj. Now I think you might understand why I'm writing the indices on top and bottom. Otherwise, it will become confusing to see which index you are exchanging and which index you are keeping the same. RJBK, RMBN, and so this will give you RM, BN, RM, BN minus RN, BM times RMB, which is equal to R square B square minus R dot B square. And this factor is 1, by the way. So we can just set it to 1. So finally, our term, our diamagnetic term becomes Q squared by 8m R square B square minus R dot B square. Now in this expression, you can insert your magnetic field. Your magnetic field is what? B is equal to B naught times Z hat, right? So if you substitute that expression in here, what will you get? You will get B square times R square minus and r dot b square will give you b square times z square. And so this will give you b square times x square plus y square. That's what this term will be. So finally, we can write down our Hamiltonian minus h bar squared by 2m gradient of psi.
We get a diamagnetic term, which is q square b square by 8m plus sign q square b square by 8m times x square plus y square plus q times phi, and then minus our paramagnetic term, which is minus q by 2m b dot a psi. Okay, and hat on this L to indicate that it's not. Okay, and what is B dot L? B dot L is equal to B naught times LZ, right? Because B only has one component, that's along the Z direction. Right? Okay, so now what we can do is, we are looking at this constant uniform magnetic field. Now we have to decide what is our, this gives us a vector potential, right? Now we need to decide what is our scalar potential. So for the scalar potential, we have two possibilities. Well, there are an infinite number of possibilities. Just please pay your respects to the little monster. Wave karo, wave kare.
Come now. Come here.
Okay?
Very bad.
Thank you. Bye.
Sorry.
No problem, dear.
Come. Sachi.
Say you. So we consider two cases. We consider this thing, which are the cases of immediate interest, right? Hydrogen atom, and in this case, our external potential, the electric potential V is equal to minus KQ, KQ, our potential energy, not our potential, right? No, sorry, potential, minus KQ by R. And so phi times Q will become minus KQ square by R. And the other example is the free electron. So free meaning there is no external electric field. This we can set to 0. Okay. All right. So one thing we can see immediately without going into all the mathematics, right, is what is the effect of this term, right? So let me write down my Hamiltonian as H naught plus HB1 plus HB2. Okay, what is H naught? H naught is my kinetic term plus Q times phi times psi, and of course all of this should be multiplied by psi. Then HB1 is this expression over here, the diamagnetic term, and HB2 is the paramagnetic. Okay. So one thing we can see is, let us consider the case when this expression I write as B times Lz. So we consider the case when the angular momentum eigenvalue is 0. Right? So when this is the case, then what is H? H will be equal to H0 plus HP. Right? What is the other possibility? The other possibility is that your angular momentum is not 0, right? So this could be, let's say, plus or minus h bar psi. So the moment you introduce this term, what you are doing is you are lifting a degeneracy. So this this Hamiltonian h prime is equal, if you just look at h naught plus hp1, this has two degenerate ground states, and that has something to do with this something called the with the time reversal invariance of the system. So when you introduce angular momentum, what happens is, and you couple it to the external magnetic field, you break the time reversal invariance. And breaking the time reversal invariance causes this degeneracy to be lifted, meaning that degeneracy is removed. And what happens is that now your Hamiltonian can be written as this h prime plus hb2, right? And now this will give you whatever is the energy eigenvalue of h prime plus a state. So if you have some state here, this is the energy eigenvalue of h prime being h naught plus hb1. And if you have an angular momentum, right, you'll get two states. One is E plus delta E, one is E minus delta. Right? So in the presence of a magnetic field, what will happen to the spectral line of the hydrogen atom? So you have an electron, right? Depending on whether it's going around, in this direction commensurate with the magnetic field, right? So let's say this is the external magnetic field. If it's going in this direction, so this would be counterclockwise. So your L is pointing in the same direction. You would have E minus delta E, right? And the other direction, you would get E plus delta. Right? So this is what is the source of the Zeeman splitting of the spectral line. And again, you might say at this point, well, we're talking about quantum mechanics, and the electron has a wave function, so I can't talk about it going around in this way and going around in that way in any fixed orbit. And yes, that is completely correct. But so I'm just using this sort of classical description to give you the physical picture. Right? So when I say that the electron is moving in this direction, it's not really like this. Angular momentum eigenvalue is positive. and the other one the angular momentum eigenvalue is negative. Okay. So this is the Zeeman effect. Now, what else can we consider? We can consider what happens if you have unbound electrons. So let's look at these terms here, right? Let's try to look at what is the magnitude of their contribution to the Hamiltonian, right? So whenever you have, so this is a very general sort of procedure, right? Is that you can write some Hamiltonian, any Hamiltonian, right, as something like this, let's say, and so on, where H1 is one set of operators, H2 is another set of operators. And what is G1 and G2? G1 and G2 are some sort of coupling strengths, right? So in this particular case, for instance, what would be the coupling strengths? Well, this would be one of the coupling strengths, right? And here the other coupling strength would be given by this Q times B by 2n, right? Because the eigenvalue, this L times psi just gives you a factor of, well, you should include that factor, that gives you H bar. So we can look at what we expect the contribution of these two terms to the Hamiltonian to be, right? So, you can have a situation when G2 is much greater than G1, for instance. And in this case, obviously the dynamics would be determined. Well, you would have to look at the dynamics, right? This would give you certain case, this would give you a certain kind of dynamics. The other case would give you a certain kind of dynamics. So let's look at what these two terms are capable of. All right. So we have this term here, and we have this term here. So let's do a comparative study. And such comparisons are very useful, okay? Because so this is the first term, the diamagnetic term. Let me call it HD psi. And this is the paramagnetic term. Let me call it HP psi. Right? So if you want to estimate the relative strengths of these two, one way to do that is to take the expectation value of, let's say, HP and HD, and then divide. Right? Now this expectation value is being taken for some arbitrary state, okay, and that state does not necessarily need to be a solution of this full Hamiltonian. Remember that if you are given a state and an operator, you can take an expectation value. You don't need to worry about what that state is a solution of or not, okay? And in this case, we don't need to do all of that because we are looking at order of magnitudes, right? So if you look at H paramagnetic and you look at the expectation value, well, the minus sign doesn't matter, obviously. You get Q by 2 pi, then you will get the magnetic field. And then you have the expectation value of the LZ operator, right? And the diamagnetic term, we have Q square B square by 8m, right? And then you have the expectation value of this x square plus y square, right? These are also operators, right? X square plus y square. And now we can ask ourselves, for instance, that for atomic hydrogen, okay, in the ground state, or maybe in the yeah, in the ground state, sure. Right? What do we expect LZ to be? LZ would be of the order of h bar. And what would we expect this x square plus y square, the expectation value of this? This would be of the order of the Bohr radius squared, right? A naught. It's approximately the size of the Bohr radius is the size of the ground state orbital, right? It's like 1 point something times A naught if you take the actual expectation value of the hydrogen atom Hamiltonian, but we'll just approximate it as A naught square. And so if you insert these expressions in this, what do you get? H para, H diamagnetic. Well, we do some cancellations. Let's see. N cancels out. Sorry. One factor of B cancels out. One factor of Q cancels out. So you will get 4 divided by QB and 4 H bar QB inwards. Right? And now you can insert some numbers into this. You can insert the number of the value of A naught and H bar square, for instance. Right? And also Q is the electronic charge, right? So if you just do an order of magnitude, so 10 to the minus 34, 10 to the minus 19, this is 10 to the minus 20 because A is 1 angstrom, 10 to the minus 10, right? Times B. Okay. So what do you get? You get some 4, we can ignore that. Again, we are interested in order of magnitudes. So we get 10 to the minus 34 by 10 to the minus 39 times B, which is something like 10 to the 5 times B. So maybe it's better to write it as HD by HP instead, in which case we get 10 to the minus 5B. And right, so this is 10 to the minus 5. B is in units of Tesla, or whatever the units you want B to be. So essentially, unless your magnetic field is humongous, right, the diamagnetic term will be negligible compared to the effect of the paramagnetic term. But you could ask what happens for free electrons, right? So for free electrons, the angular momentum eigenvalue is 0, right? I mean, if you take them to be free streaming, in which case the diamagnetic term is going to be more important. Okay. So what else? Right. Yeah. One more thing, we can look at this paramagnetic Hamiltonian minus Q by 2m B dot L, right? And we can write this as minus B dot mu, where mu is the magnetic dipole moment operator, which is Q by 2m. Okay, or maybe there is a negative sign. There might be a negative sign here somewhere. see, minus sign plus beta. Okay, so this is the magnetic moment. Now this is again the magnetic moment due to the orbital motion. Now what happens due to this magnetic motion, I've already explained. You get this splitting, but we can look at it a little bit more carefully, right? We can ask what happens when we include this potential. Which potential was that? The central potential phi. We have not included the effects of the central potential, right? So I'll do that in the next class. Okay, I'll stop here for now. Okay, questions? So this is, see, we are working our way up from this, starting from the Hamiltonian, the classical Hamiltonian, to the quantum Hamiltonian. And then the next step is to introduce the spin, the internal degree of freedom. And then once we have the spin Hamiltonian, then the next step is to talk about the relativistic electrons with spin, and that requires the direct equation. So let me just show you this, this, what do you call it? Image of the Zeeman effect, right? So this is the paper, the original paper, right? 1897. So you have 3p and 3s, right? Which one is going to be 3p and which one is going to be 3s? Any ideas? So if you look at these lines, right, this line, it splits into two, but then those two are again split into two smaller lines. So this is the 3s state. So the s state, remember, has an eigenvalue. Of the, right, so the angular momentum eigenvalue can be +1 or -1. For the p state, the eigenvalue can be +1, 0, or -1. So you get one line in the middle and then two lines over here, right? But then there is a further splitting of those two lines. So you have to talk about other effects also than what we have considered. Okay. All right. So I'll stop here for now. Are there any questions? Okay.